we saw how we can manage individual resources with Crossplane. If, for example, we want a virtual machine in AWS, Azure or Google Cloud, all we have to do is define a Kubernetes resource that represents it. Apply it to the control plane cluster running Crossplane, and that's it. Crossplane takes care of everything else. The problem with that approach is that it is often very low level. For example, creating and managing a production-ready database can consist of quite a few low-level resources that require a certain level of expertise that not everyone in an organization might have. Most of the resources we are managing today are low-level. There is no such thing as a database in AWS. Instead, we need to combine RDS with the VPC, with subnets, and with gateway, and so on and so forth. Even if we do all that, we still need at least one database inside the database server, a user, and a schema. Similarly, there is no such thing as an application in Kubernetes. We need to combine a deployment with an ingress, with a service, with secrets, and quite a few other resources. The same can be said for almost anything else. Software, services, and infrastructure are complex, and providers we are using are intentionally focusing on low-level services so that they can cater wider audience. Resources are more like building blocks than final solutions. On the other hand, we are all trying to shift left. One of those directions. We are trying to enable our colleagues to be autonomous instead of waiting for someone else to assemble those building blocks for them. As a result, we need to use experts in certain fields to create services that can be consumed by others. A database expert can create services that will enable others to manage databases in a way appropriate for production. A Kubernetes expert can create abstractions that define what an application is. A security expert can bake security and policies into those services. There are many other examples, and it all boils down to experts in certain fields using their experience to create and manage services that can be consumed by others. The end result is an internal developer platform that exposes services that simplify workflow for developers and other software engineers. That's where Crossplane compositions come in. They enable us to define what something is. They enable us to codify our expertise and expose services as higher level abstractions. In this video, we will explore how to leverage Crossplane's ability to create custom resource definitions and controllers that will act as such services. The setup for this video continues using the pattern from the previous one. We will enter into the directory of the forked repository and start the Nix shell that brings all the tools we will need. Next, we will make the setup script executable and execute it. The only thing left is to source the environment variables in case we need them later. And now we can explore composite resource definitions. Crossplane compositions consist of a few components. There are composite resource definitions, compositions, and composite resources. Right now, we will focus on the first of those. We will create a composite resource definition. For now, the only important thing to know about composite resource definitions is that they extend Kubernetes API by creating custom resource definitions. They enable us to define what something is. I'll explain everything else you need to know about them in a moment. For now, let's take a look at a simple example which we will improve as we are progressing through this video. Everything we do with Crossplane is defined as Kubernetes resources, and composite resource definitions are no exception. The API version, kind, and metadata should be self-explanatory if you have at least a basic understanding of Kubernetes. If you don't, well, I'm surprised you got this far without giving up. The magic is in the spec. The first in line is the spec group field that defines the API group that will be created in the Kubernetes API. That follows the rules that any Kubernetes resource definition must follow. Deployment, for example, is in the group apps v1. By defining groups, we are making sure that resources are uniquely identified, even if some of them have the same kind. Further on, there is spec names. That defines the names of that resource definition, both in singular and plural. You can probably guess what the goal of that definition is by looking at the names kind value. We will use it to define SQL or database servers and this is important, and everything they need. I will leave the claim names fields a mystery for now. We will explore them later. Finally, there is versions that, as the name suggests, defines the versions of that resource. It can be anything, but my recommendation is to follow Kubernetes versioning guidelines with V1 Alpha 1, V1 Beta 2, V1, and so on and so forth. Further on, there is served, which essentially tells Crossplane whether that specific version is served to users or whether it's enabled. Then there is referenceable, which indicates which specific version is currently active, or to use Crossplane terminology, which one can be referenced. A composite resource definition can have any number of versions, but, and this is important, only one can be referenceable. Finally, there is arguably the most important field, schema, which is based on OpenAPI. I intentionally left it blank in an attempt to create the simplest possible definition, which we will expand later. Before we proceed, please bookmark the Crossplane API page. You will find the complete schema for composite resource definition or any other Crossplane API over there. By doing that, by redirecting you to the docs, I can avoid going through every single API in detail and risk repeating details written over there. Now, let's apply the definition and retrieve it from the control plane cluster. Over time, you will probably get tired of typing long resource kinds like composite resource definition, so you can also use short names like, in this case, XRD to get the same outcome. Now, I will continue using long names most of the time simply because I believe they are easier to understand even though they are harder to type. For now, the main takeaway you should get from composite resource definitions is that they create and manage Kubernetes custom resource definitions, which is a way to extend Kubernetes API. As proof that's exactly what they do, we can list all CRDs. We can see that a specific composite resource definition created 2 CRDs. We will ignore the first one, the one that says SQL claims, for now, and focus on the second, SQLs. One nice thing about Kubernetes CRDs, and through them about Crossplane composite resource definitions, is that they are discoverable. We can, for example, ask Kubernetes to explain SQLs. The ability to retrieve a schema, or as in this case, to explain it, might not sound very exciting, but if that's what you think, I will have to strongly disagree. Kubernetes API allows us to discover the type of resources we can use and their schemas, and that means that attempts to visualize them through UI, CLIs, or any other means is trivial. It would be trivial to build a dumb frontend that would be able to discover what is what, to help us define resources, and to operate those resources. With the standard but extensible API like the one Kubernetes offers, we can easily build the tools we need for an internal developer platform. We will explore that in more detail in one of the next videos. For now, the key takeaway is that everything in Kubernetes is discoverable. And since Crossplane is Kubernetes native, everything we do with Crossplane is discoverable as well. From now on, we can create any number of resources based on that definition. We are yet to discover whether that also means that we can create any number of database servers, SQLs, but that's coming. Here is one example. That manifest is a resource based on that definition. Values of the API version and kind fields match those of the definition. Metadata contains an arbitrary name that can be anything as long as it is unique, at least within the given namespace or not namespace. We'll get to that later. Finally, we did not set any spec fields in the definition, so that one is empty, for now at least. All that's left is to apply that SQL and celebrate. We got our first SQL server. Our first database was born. Let's take a look at it by listing all SQLs. That does not look right. My DB is not synced. Crossplane could not even start working on it. We can confirm that nothing really happened by outputting managed resources. And surprise, surprise, there are no managed resources. Crossplane did nothing. And that was to be expected. All we did so far was to define a composite resource definition, or XRD, which essentially created a Kubernetes custom resource definition, or CRD, which extended Kubernetes API with a new resource type called SQL. There is no controller that would detect composite resources, or in Kubernetes terminology, custom resources. Simply put, we extended Kubernetes API, but we did not tell it what to do when resources based on that API are created. What we are missing is crossplane compositions. Right now, we have none, and we can confirm that by retrieving all compositions. So, for now, we can create as many SQL resources as we want, but there are no controllers, so there is no process that will do anything with those resources. They're just entries in etcd. The output shows no resources found. Let's fix that. Let's tell Crossplane what to do when a resource based on our definition is created. Before we proceed, let me state that I chose to use Google Cloud in this video. The first video used AWS and the second used Azure, so now it is time for Google Cloud. That being said, just as in previous videos, you can use any of the big three hyperscalers. Explanations in this video will be based on examples for Google Cloud, but the logic is the same no matter which one you chose, so you should not have any trouble following along, even if what you see in your terminal is different from what you see here in this video. With that out of the way, let's take a look at the composition I prepared in advance. This is a definition of composition. Think of it as one of the implementations of the definition we applied earlier. We have metadata with a name and labels. Those are important since, as we will see later, they will allow us to choose which implementation we want to use when we declare a composite resource. You'll see those in action later. For now, remember that this composition can be identified through a name or labels, which in my case are set to provider Google and DB PostgreSQL. Next, there is composite type ref, which tells Crossplane what the associate composite resource definition this composition is associated with. In other words, this composition, this implementation, will be used whenever someone defines an SQL that has matching name and labels, or labels, not and, name or labels. We'll see how that works soon. For now, let's take a look at the second component in the spec. Spec resources array contains the list of resources that should be managed whenever someone defines the SQL resource. In the case of Google Cloud, there are only 2 resources. If you're using AWS, you'll notice that there are many more, since AWS often forces us to combine more resources to get something meaningful. Each resource has a name and a base. The name is a unique identifier within a composition, while the base defines all the details of a resource that should be managed by that composition. In the case of Google Cloud, we're defining a database instance and the user. Those two are essentially managed resources, just like those we used in the previous video. The major difference is that we are not defining those resources every single time, but instead grouping them all together, and by doing that, creating a new service and exposing it to others. Next, you will notice selectors, like in the case of Google Cloud Instance Selector. Selectors deserve special attention, so we'll go through them separately. For now, think of them as Crossplane's way of saying, let this resource get some information from this other resource or a group of resources. The important part is that, among other things, we are defining root password secret ref. That references a Kubernetes secret that will contain the initial password for the database. In the case of AWS, that would be password secret ref, and in the case of Azure, it is administrator login password secret ref, I think. For now, remember that a secret with the password is required. We'll need that knowledge later. The rest is following the logic we explored in the previous video. Each resource defines specific parameters like the region, database version, and so on and so forth. As a result, we should have a database server with everything it needs. Actually, no, wait, stop. That's wrong. That database server will not have everything we need, but rather it is a start that leads us towards the path that ends with everything we might need. Even though my examples are based on Google Cloud, that is only one of the three compositions we're defining and relating to the composite resource definition. We can see that all three of them are in the compositions directory. We are about to apply all the manifests in that directory, and as a result, we'll get the definition that we already applied, and three compositions, one for each major hyperscaler. We can see that three compositions, AWS PostgreSQL, Azure PostgreSQL, and Google PostgreSQL, were created. As a result, Crossplane can spin up a controller that will manage resources based on that definition. And we will see the controller in action in a moment. We can also notice from that output that we got quite a few warnings. The definitions of individual resources that constitute compositions are not available. Just as we did in the previous video, we need to apply providers that contain definitions behind those resources. Later on, we'll see how we can package compositions into configurations that will auto-install the required providers. But that's the story for later, for some other time. For now, we will apply the providers manually. They're defined in the providers SQL v1 YAML, so let's take a look at it. Over there, just as we did in the previous video, we have a few providers. There are EC2 and RDS providers from the AWS family. We need both since RDS or SQL in AWS requires some EC2 resources as well. Then there is SQL provider from GCP and DB PostgreSQL from Azure. Now, let's apply those and take a look at package revisions. As we saw earlier, each of the providers can have any number of resource definitions, so we might end up with hundreds of CRDs. As a result, it might take a while until they're all loaded and ready to go. So we might need to wait for a bit until we see the status of all the providers as healthy. After a while, once all the providers are healthy, we can rerun kubectl get package revisions. Now that all the providers are healthy, we can proceed to configure them. Here's the configuration for the provider that matches your choice of the hyperscaler. I mean, it matches mine on the screen, but when you follow the instructions and the instructions are in the gist, you will see that they match whatever you chose. We already learned in the previous video how to work with providers, so there's probably no need to explain that provider configuration. The only important note is that even though we are creating compositions for all three hyperscalers, we will configure only one of them, since that should be sufficient for what we are about to explore next. So let's apply the provider config and retrieve the compositions we created earlier. All three compositions associated with the SQL kind are up and running, and we can finally start managing database servers. To do that, we will have to modify the composite resource we used before. Here's the updated version. To begin with, we're defining a standard Kubernetes secret that contains the password that will be used as the initial password for the database server. We already saw the reference to that secret when we explored the composition itself. Besides the secret, there's a modified version of the SQL definition we created earlier. While the spec field was empty before, now it contains composition selector. That's one of the ways to select which variation, which implementation of the SQL one wants to use. In this case, it is clear that it is Google Cloud, but it could be AWS or Azure as well. The interesting thing about that SQL definition is that we are letting consumers of the service choose what they want without having to deal with all the implementation details. A user could choose to run a database in any of the major hyperscalers with a change to the provider label. What will happen in the background is completely different, since each hyperscaler works differently. Yet, to a user of the SQL service, it is all the same. Those differences are becoming implementation details he or she does not care about. If we created additional compositions, we could have enabled people to choose between, let's say, PostgreSQL and MySQL or anything else we want. Still, for the sake of keeping this video relatively short, I did not include additional compositions. PostgreSQL running in AWS, Azure, and Google Cloud should be more than enough, at least for now. Another thing you will notice is that we are not letting users choose anything but the provider. We could create a better experience by, for example, letting people choose the size of the database server or the version of PostgreSQL. We might actually do that later. For now, we are keeping it simple. The only choice that can be made is the provider. So let's apply the secret and the SQL composite resource and execute Crossplane trace. We explored it in the first video to see the SQL and all the child resources it might create. In the case of Google Cloud, we can see that SQL MyDB created two resources, database instance and user. Both are not ready, and the status says that it is creating them. As a result, the parent resource MyDB is also not ready. It will take a while for all the resources spun up from the SQL Composite resource to be ready. How much it takes varies from one hyperscaler to another, as well as the number of resources that should be created. Now, take a break. Go get some coffee. When you're back, the process should finish on your laptop, at least if you're following along, and we will be able to execute Crossplane trace command again. And I will just fast forward. The status of all the resources is now available. We did it! We did it! We managed to create a service that enables everyone to create and manage PostgreSQL in any of the three major hypervisors, and we made it as easy for them as it can get. If you're a skeptic and you do not take my word for granted, you can open the console of your favorite hyperscaler and see that the database server and all the related resources are indeed up and running. So, what did we build just now? We created compositions for SQL database servers in AWS, Google Cloud, and Azure. Crossplane, in turn, created a controller that watches for composite resources. From now on, when someone applies a composite resource to the control plane cluster, the controller will expand it into all the managed resources required to run the PostgreSQL server in the selected hyperscaler. If, for example, the match labels provider is set to Google, the Crossplane controller will expand the composite resource into managed resources required to run the database server in Google Cloud. Similarly, if someone applies a composite resource that sets the provider to AWS, the controller will expand it into managed resources required to run the database server in AWS. Now, to be honest, what we have done so far is far from perfect. Consumers of the SQL service have no influence over the outcome. All Crossplane resources are cluster scoped, which is far from perfect and potentially insecure. Database servers we are creating have no databases inside them, and quite a few other things. We will fix or implement all of those and quite a few others. We just started. From now on, we will be improving those compositions until we reach perfection. The first thing we should fix is the selectors we used. Let's get back for a moment and take a look at one of the definitions we used in the previous video. The instance resource is referencing the network through the network ref set to hard-coded DOT network. Essentially, we told Crossplane that it can take the information it needs, for instance, from the network resource named DOT network. That worked, but that wasn't necessarily the best way to reference a resource. We used a better approach earlier in this video when we defined the compositions. So let's take another look at what we did and what I did not yet explain. In this case, the user resource needs information about the database instance where the user should reside. Since, among other things, Crossplane automatically injects labels Crossplane.io composite into all resources managed by a composition, we use that one to tell the user how to find the database instance. That, however, is a bad solution. It contains the hard-coded value MyDB. If you created a composite resource named anything else, the user would either fail to find the database instance or it would find the wrong one, the one from some other composition. Fortunately, there is a much better and easier way to reference resources within a composition. So let's take a look at an updated version of the composition. This time, instead of referencing or selecting resources using names or labels, we're setting match controller ref to true. That can be translated to, if you need information from the database instance, find it yourself. It's somewhere in the composition. Don't ask me how to find it, figure it out. More often than not, match controller ref will be the main, if not the only way you will reference managed resources within a composition. Nevertheless, that's not the only way to select resources. We will explore others later, and if you're impatient, you can consult the documentation. All that's left is to apply modified compositions. You will not notice any tangible change to manage resources, since the change we just applied is only a better way to accomplish the same result as what we had before. If we created a composite resource that was not named MyDB, then we would see a different outcome, since the previous version would fail due to the hard-coded MyDB selector. Next, we will explore patching, which is probably one of the most important features of compositions. Patching enables us to customize the experience, but before we dive into it, we will delete the composition and, through it, all the child resources it manages. Wait, there is one more thing I want to show by listing all the managed resources. We need to do that before all the resources are actually removed. Take a look at the names of the resources. My database instance is called MyDB and then few random characters. That's bad. A small annoyance is that we might want to have predictable names for Kubernetes resources. Maybe we would prefer it to be called MyDB without the randomized suffix. More importantly, that is the name of the database server that was created in Google Cloud. You can observe that through the external name column in that output. We should be able to name resources any way we want, right? As a matter of fact, that will be a good example we can use next when we explore patching. You should now wait until all the resources are deleted before moving on to the next section, right? I will not wait for it because I will just fast forward. The time has come to extend our composite resource definition. Let's say that we would like to enable users of our database as a service solution to be able to specify the version of the database and the size. To make it more interesting, we will try to avoid people having to know what are all the available sizes in AWS, Azure, and Google Cloud by allowing them to choose from 3 sizes: small, medium, and large. We will figure out how to map those sizes to the correct values in the hyperscaler they choose. How does that sound? Sounds good? Let's try it. A potential solution is in the updated version of the definition, so let's take a look at it. The previous version had the OpenAPI v3 schema empty. Now it defines 2 fields, ID and parameters. While ID is a string, parameters is an object, meaning that it contains additional fields, version, and size. Besides definitions of the fields that form the schema, version and parameters fields are set as required. Everything we defined in OpenAPI v3 schema follows the same rules as those we would follow when defining Kubernetes custom resource definition. So the experience required to write composite resource definition is the same as creating custom resource definition, plus a few additional fields which we might comment on later. And that's it. That's all there is to it, for now at least. So let's apply the modified version of the definition. Now that we introduced a few additional fields in the composite resource definition, we should modify our compositions to take advantage of those changes. Let's take a look at the modified version of the composition. There are a few changes we should discuss. So I'll break the output into smaller pieces. To begin with, there is patch sets with a name and a list of patches. Those happen to be using the most common pattern for patching with from field path and to field path. We can translate those as take annotations value from the composite resource and put it into annotations of the managed resource. So whichever annotations we defined in the composite resource will be the annotations propagated to the managed resource. As you already know, annotations are standard Kubernetes fields available in any resource. A more interesting patch is the one that takes ID and puts it into metadata name. Actually, there is nothing special about it from the patching perspective. Take the value from the parent resource and put it into a resource managed by that composition. What makes it interesting rather than special is that ID is a custom field. That's one of the fields we added to the new definition as a way to enable users to specify a unique identifier for database resources. I mentioned that a patch like the one we're discussing, and there are other types, takes values from the composition resources and puts them into resource managed by that composition. However, that patch set does not specify which resources will be patched. We'll see how to tell Crossplane which resources to patch soon. Right now, we will move to the next change. Not only that parts of that composition were added or updated, but some were removed. For example, the root password secret ref name from the Google composition is now gone completely. In the previous iteration, it contained the hard-coded value mydb password. And we already established that hard-coded values are not a good idea if they differ from one resource to another. The name of the secret that contains the password should not be mydb password, but the name of the composite resource, whichever one chooses, and with the suffix -password. So I removed the hard-coded value, and we will see soon what we'll use instead. Similarly, database version that was set to hard-coded value PostgreSQL 13 is gone as well. The value of that field should be replaced by whatever someone chooses to put as the value of the version field be added to the definition. The same is true for the tier. It's gone as well, and it should be replaced with the size. This is the part where we patch specific resources. The first one in the Google composition, SQL, got the patches section that has the type set to patch set, followed with by the patch name set to metadata. That's where the patch sets we commented on earlier are used. Instead of defining repetitive patches over and over again, we define them as patch sets, and now we're telling Crossplane to apply them to the SQL resource. As a result, the annotations and the name will be patched with values from the composite resource. The next patch contains from field path and to field path, just as those we saw in patch sets. Its goal is to replace the database version in Google Cloud Managed Database with whatever someone chooses to be the version. But there is a problem. What we expect users to specify something like 13 as the PostgreSQL SQL version, Google Cloud expects it to be something like Postgres_13. Now, I do not want to force users to deal with the intricacies of specific hyperscalers. Instead, I consider it my job to translate expected input, which is 13, into input required by a hyperscaler, and that should be Postgres_13. To mitigate that, the second patch adds transforms to the mix. In this specific case, it can be translated to transform the input value defined as a string into this format, Postgres_ and then whatever the value is, which is %s. As a result, %s will be replaced with whichever value is retrieved from version. So, apart from retrieving the value from one resource and using it to patch another, we are also applying a transformation, which in this case is to format a string. The next one is also using a transformation, but in a very, very different way. It takes the size value and uses it to patch the tier field. That's the size field we added to the definition, and as you probably remember, the goal of the size field is to allow users to specify whether they want a small or a medium or a large database server. Now, as you can probably imagine, hyperscalers have a large variety of sizes we can choose from, and none, and I repeat, none of them is small, medium, or large. So we have to do the translation, and that's why this patch has type set to map. It allows us to map an input value into something else. It acts as a map in any programming language. In this case, we are telling Crossplane that it should convert small to db custom 1, 3840, medium to db custom 16, and large to db custom 64. If you're looking at AWS or Azure, you will see a similar mapping, but with different values. They're based on the sizes those hyperscalers offer. There are a few other patches, but they all follow the same pattern, so there's probably no need to go through them. Instead, we'll apply modified compositions before we see them in action. Finally, we can incorporate those new capabilities into the composite resource we use so far. Here's the updated version. We added a few metadata annotations so that we can test that one of the patches we defined works. Further on, ID and parameters version and parameter size fields were added as well. That manifest can be translated to give me a PostgreSQL server in Google, make sure that the version is 13 and make it small, without making me learn which nodes in Google classify as small. The user, the person who defined that manifest, gained more freedom to specify what matters while still not having to deal with low-level details and intricacies of the hyperscaler of choice. If you're using Azure, you will notice that we changed the name from MyDB to MyDB2. Azure does not allow repeated names for some of its resources like SQL, even if those resources were deleted. So the ID changed to MyDB2. Otherwise, since we already have MyDB and deleted it, it would fail to create a new one with the same name. Let's apply the composite resource and trace the progress. Those resources will eventually be ready, and while waiting for that to happen, we can make a few observations. To begin with, the names of managed resources are now MyDB. There is no auto-generated suffix anymore. We got that change because one of the patches made sure that the name of a resource is the same as the value of the new ID field we added to the definition. Using auto-generated suffixes is actually a good practice that helps us avoid conflicts, but I like my resources to have proper names, so we ignore the best practice. Next, we'll check whether the annotations we added to the composite resource were indeed added to managed resources. To do that, we'll create a new environment variable XR with the full name of any of the managed resources we created. And we'll output that resource as YAML. We can see that the managed resource was indeed patched with annotations from the composite resource. Now, feel free to confirm that other patches were applied as well, or simply trust me when I say that they all did. The size and the version we specified were applied to the relevant resources. Now that the PostgreSQL server is up and running, we need to figure out how to connect to it. Otherwise, what is the point of having a database that cannot be used? We have a PostgreSQL database, but right now it is just sitting there, not being used by anyone or anything. We need a way to connect to it. Fortunately, Crossplane can combine all the secrets generated by the managed resources into a single Kubernetes secret. All we have to do is tell it where to put that secret. Let's take a look at the modified version of the composition. To begin with, we are telling Crossplane through write connection secrets to namespace to store the secret that contains all the confidential and connection information generated through managed resources in the Crossplane system namespace. Think of that field as being the default location for the secret, which can be overwritten by specific resources. Further down, we are overwriting the namespace where the secret will be stored through the namespace value. That wasn't really necessary since the value Crossplane system is the same as what we set through the write connection secrets to namespace. But I wanted to show that we can overwrite the namespace for the secret from that specific resource. That capability will become important later when we switch to namespace scoped resources. Finally, since it would be silly to have all SQL secrets with the same name, we are using patching to set the value of name of that resource to whatever the ID is in the composite resource. And that's it, for now at least. So let's apply the composition and output the secrets in the Crossplane system namespace. We can see that besides the MyDB password secret we created in the way to provide the initial password, there is now MyDB that should contain all the information on how to connect to the database server. We have a slight complication with the demo since the database and the secret are called MyDB if you're using AWS and Google Cloud, and MyDB dash with a timestamp suffix if it's Azure. To mitigate that discrepancy, we'll store the name of the database to an environment variable. Locate the secret with the name that starts with MyDB and has a timestamp suffix if you're using Azure. Copy it and use it as the value of the command that follows. For everybody else, it's just MyDB. Now we can retrieve the secret and output it to YAML to get a sneak peek into the data it contains. The output will differ from one hyperscaler to another since the information each provides and the keys used to represent that information might be different. We'll see later on how we can unify that. For now, what matters is that all the information is available. In the case of Google Cloud, we can see that, among other information, the password and the public IP are available. As you probably already know, data in Kubernetes secrets is base 64 encoded, so we need to decode the data if you would like to use it to connect to the database server. We'll do that soon. We created a database server, so the next logical step would be to try to connect to it and confirm that it works as expected. We'll get the information like the user, the password, and the host from the secret Crossplane provided. Since we have not yet unified the format of that secret, the commands might differ from one hyperscaler to another. Let's start with the user. Next, we'll retrieve the password. Then we'll get the key that holds the host in the secret. Finally, we'll use that key to retrieve the host itself. And now we are ready to connect to the database. Since I did not want to assume that you have pSQL on your laptop, and since I was too lazy to add it to shell Nix, we'll run it inside the container based on the Bitnami PostgreSQL image. Once inside the container with pSQL, we can execute the command that connects to the remote PostgreSQL server and list all the databases. We have a problem though. We can see system-level databases inside that server, but not one that we would use from, let's say, an application. We should try to extend our compositions to add a database to the PostgreSQL server. And while we are at it, we might just as well extend them to provide a unified format for the secret we are generating. So let's get out of pSQL shell and out of the container. Right now we are missing a way to generate a database inside the server and to create a uniform secret with the information on how to connect to the database. We cannot do either of those tasks with the providers we are currently using. AWS, Azure, and Google Cloud providers do not have resource definitions for those types of operations. Fortunately, other providers can do just what we need, and there is no limit to which resources we can include in compositions. The fact that, let's say, one of the compositions manages PostgreSQL in Google does not mean that we are limited only to what we can do through the Google Cloud API. We can, for example, include the SQL provider to manage databases inside database servers, and we can add the Kubernetes provider to create any Kubernetes resource, including the secret we discussed. Let's take a look at yet another version of the composition. There are 4 new resources in that composition, so I'll break the output into smaller pieces, one for each of those new resources. We can add a database through the SQL provider. For it to work correctly, it needs to be configured so that it can authenticate to the PostgreSQL server. Hence, we are adding the provider config as a new resource to the composition. That config will use credentials from the secret we are generating. Since the secret name is the same as the value of the ID field, in the composite resources, we're patching the provider config so that the name field of the managed resource has the value taken from the ID field of the composite resource. There's one important thing to note here. The SQL provider config expects a secret with credentials in a specific format. Hence, besides the need to have secrets with credentials in the same format, no matter which hyperscaler provider we're using, this provider config forces us to use the specific format. Please note that Azure PostgreSQL server already stores the credentials in the secret with exactly the same format, so there is no need to create it separately. Hence, if you're using Azure, you'll notice that the 3rd and the 4th new resources we'll explore are missing. Now that we saw that we added provider config, which will enable the SQL provider to talk to the PostgreSQL database server we are managing, we can move on to the next new resource. This is a simple one. We are adding database managed resource from the SQL provider we configured earlier and making sure that it is using the correct configuration by patching name with the value from ID. That resource will create and manage a database with the same name as the name of the resource itself. So there is nothing special to do given the name field is patched through the metadata patch set. Let's move to the 3rd new resource. We can use object resources from the Kubernetes provider to create any Kubernetes resource, including secrets. But just as with the SQL provider, first we need to apply provider config, which will tell the Kubernetes provider how to find the cluster where it should create the secret. We are doing that by saying that the source of the credentials is injected identity, which essentially means that it should manage resources in the cluster where it's running. It could be a different cluster, and we'll explore that option in one of the upcoming videos. Now we can explore the last resource we added to the composition. That's a long one. We are creating an object which can be any Kubernetes resource. In this case, we are creating a secret with a hard-coded port set to encoded value, whichever, which in its decoded form is 5432. There is no reason not to have it hard-coded since it is always that port. The interesting part is the reference section with a few patches from. Those allow us to get information from any resources in a Kubernetes cluster, no matter whether that resource was created by Crossplane or any other process. The first one is getting a value from the user resource and adding it to the secret as the username. The second takes the value from the secret and puts it into the password. And the third one from a different secret, which will end up being the endpoint. All that might not be obvious just by looking at the patches from sections. Parts of that puzzle are in the patches, which in this case are patching patches from. We're still missing something. We introduced 2 new providers into our compositions and we need to deploy them as well, at least until we figure out how to automate that part. This time, however, one of the providers will require a bit of extra work. Let's take a look at the updated version of the providers. The first resource is easy to explain. It is the Crossplane provider SQL provider. The Kubernetes provider is a bit trickier since we need to make sure that it has permissions to create additional resources through the Kubernetes API. So we are creating a service account and cluster role binding that gives the service account permissions. Further on, there is controller config, which references that service account. Finally, the Kubernetes provider is configured through controller config ref to use that controller config. It's handful, I know, but it works. And it is pretty much how you would create service account and cluster role binding for any other non-Crossplane process that needs to perform some operations through the Kubernetes API inside the same cluster. Let's apply those providers, output all package revisions, and wait until they are all healthy. Once all package revisions are healthy, we can go ahead and apply modified compositions. Now we can go back to the container with pSQL, enter the client, and list all databases. We can see that this time there is a new database MyDB. The mission was successful. From now on, every time someone chooses to create a PostgreSQL server in any of the hyperscalers, a database and a secret with a uniform format will be created as well. Here's the summary of what we did. We created a composite resource, which created managed resources. Some of those managed resources created a database server and networking through the hyperscaler API. We had that before. What's new is that one of those managed resources created a database directly inside the database server, and the other collected information from other resources and generated the Kubernetes secret inside the same cluster. This is still not a good solution though. We need to switch from cluster scoped composite resources to namespace scoped composite claims. But before we do that, we'll remove the composite resource so that we can start over. Let's exit the pSQL client and the container, delete the composite resource, and list all managed resources. It might take a while until all the managed resources are deleted. So repeat the kubectl get manage command until you see that everything is gone. The database might not be deleted if the database server it was created in ends up being deleted first. That issue will be fixed later, I promise, when we explore Crossplane usage. Execute the command that follows only if the database resource is left, dangling, hanging. And now we can discuss composite claims. All the resources we created so far are cluster scoped. That means that they are managed on the cluster level and not inside namespaces. That is potentially problematic since namespaces are typically used to separate teams or types of resources, apply RBAC and policies, and quite a few other things we normally do in Kubernetes and that we will explore later. The bad news is that we cannot change the scope of composite and managed resources. They are always cluster scoped. However, we can add new types of Crossplane resources to the mix. We can use composite claims, which are namespace scoped, and which can be used to create composite resources. Not only that, but with claims, we can also have more control over the location of secrets, objects, and other namespace scoped resources. As a matter of fact, we already defined everything we need to use claims, but I sneakily avoided mentioning those parts. Let's take another look at the composite resource definition we applied earlier. The spec names field is the one we used as the kind of the composite resources. Just below it is the spec claim names, which does the same, but for composite claims. That's it. There is nothing special we have to do. With spec claim names, we can create namespace scoped claims instead of going directly for the cluster scoped compositions. All we have to do, in this case, is set kind to SQL claim instead of SQL. Hence, we could create a claim right away, but we won't do that just yet. Instead, we'll make a few modifications to our compositions. Specifically, we will change compositions so that the secret with database authentication is created in the same namespace where we will apply the claim. Let's take a look at the modified version of the composition. This is a very straightforward change. The spec write connection secrets to namespace entry that was previously set to hard-coded Crossplane system is now gone. Gone, no more. Similarly, all the places where we had namespace set to Crossplane system are gone as well. We don't want secrets to be created in the Crossplane system namespace anymore. We want them to be in the same namespace where claims are created. So we replaced those hard-coded namespace values with patches. Crossplane will automatically add spec claim ref namespace to all composite resources created by claims. So we are using those in patches to populate namespace fields. And that's it for now. We can proceed and apply changes to the compositions. Next, we'll make two tiny modifications to the composite resource we used so far. So let's take a look at the modified version. The first thing you'll notice, even though it is not in the output, is that the metadata namespace entry in the secret is now gone. That's the secret we're using to define the initial password, the one we'll get rid of later. From now on, that secret will be created in whichever namespace we choose to run the claim instead of the Crossplane system namespace. We already modified the composition to know how to fetch it through patches that retrieve the value from the namespace field in compositions. The second change is that the kind field is now SQL claim. It was SQL before, right? We specified in the composite resource definition that composite resources, which are cluster scoped, have kind SQL, and claims have it set to SQL claim. Those can be any names, and you do not have to add claim as a suffix, but you do need to make them unique within the same API group. And now we can apply the claim by executing kubectl apply. What makes the command different is that this time we're specifying -- namespace so that the secret and the claim are created in a specific namespace. As a result, we can retrieve all the SQL claims. If you try to create some kind of a developer portal, which we will do later, users would be working exclusively with claims, and we could hide access to compositions and manage resources with RBAC. That's not mandatory, but if we do something like that, we will have a clear separation between resources end users create and manage, and that's claims, and resources administrators can see, which is everything else. Those rules can be easily enforced through policies, RBAC, and quite a few other means. Hence, end users would only see the resources in specific namespaces, which in this case would be SQL claim in the A-team namespace. Administrators, on the other hand, could still see everything through, among other means, Crossplane trace commands. We can see that SQL claim created composition SQL, which in turn created several managed resources. The claim is in the A-team namespace, while all other resources are cluster scoped. It will take a while until all the hyperscaler resources are created. Once all the resources are available, we can confirm that the MyDB secret with the authentication is this time created in the A-team namespace, the same one where the claim is running, instead of the Crossplane system namespace, the one we hard-coded in previous iterations, so the composition. And there we go. MyDB secret is there. Everything seems to be working correctly. And the exploration of Crossplane compositions concluded for now. Compositions are probably the most important feature of Crossplane, and we will continue improving them as we progress, exploring other features of Crossplane, as well as the Kubernetes ecosystem as a whole. Nevertheless, we are done with this video, and we can proceed towards destruction. Please execute the commands that follow to destroy everything we did in this video. The next video will start with a fresh setup. And that's it. We are now done with this video, but not with the series. Next one is coming, or depending on when you're watching this, is already available. If it's already live, you should see it somewhere around there, above my head. Otherwise, please wait for a while until I upload it, and then it will appear there and in the description of this video and in a playlist that is also in the description of this video. Thank you for watching. See you in the next one. Cheers.